Jai Hind everyone. I am Mohan Sharma, Assistant Professor from AKGEC Engineering College in the Department of Electrical and Electronics Engineering. This video lecture is for state estimation, which is basically a topic in the subject Power System Operation and Control. Its AKTU code is KEN070. This lecture will benefit final year students of Electrical and Electronics Engineering branch and Electrical Engineering branch as well. So let's begin it. So firstly, if we talk about state estimation, so what do you understand by state estimation? Okay, so state is basically you must have studied about the state variables when in the signal systems, and then and there you must have studied what is the state. So state is basically the condition or the variables which are required for predicting the values or the future values of the system, or how the system is going to perform in near future. So this is how there are some variables into the systems. So those variables are treated as the state variables, right? State variables are there, state vectors are there, right? That was state variable analysis, and that state variable analysis dealt with some network problems, right? Basically, if we talk about the network problems, there were multi-input, multi-output systems were there, and some systems which are non-linear in nature. So linear are basically linear will be treated with the help of classical methods, but classical method means Laplace, Fourier, state, not a state variable. State variable is some which is utilized for non-linear approach, right? So if you have non-linear methods or non-linear systems are there, so you can have state variable analysis. Now, just like state variable analysis, we have states in power system. Okay, so if we talk about the states of the power system, there are several parameters, there are several values, variables by which you can calculate or you can determine the state in which the power system is there. So basically, if we talk about, there are 5 states under which the power system will be lying. So firstly, it is a normal state. So normal state is basically the normal condition under which the system will be operating as it is, whatever the conditions are required. So system is operating under those conditions, so we can say that that is under normal operating condition. Secondly, if fault is there, so if any violations is there, so under that condition the system will go to the alert mode, right? The alert state is there. From alert state you can carry system back to the normal state by just looking at or by some manipulations into the parameters, so it can be brought back to the normal state. Then comes the emergency state, right? So emergency state is the state in which the fault has occurred, and you have several values which are actually over the violation limits. Okay, after that you have extremis. Some extreme conditions are there. So in under extreme conditions, what you do, or the under the extreme conditions, and the system is totally under failure, and it has to be deal with some personals, some power system operators, so that they can go to the site where the fault has taken place, clear it, and after that clearance it can be put back to the online, right? So this is basically the system, the extremist case. Now lastly is restoration, under which the system is being restored. Okay, so restoration is basically when the system is being treated by the operating personnel, so that it can be brought back to the online. So that is basically 5 states under which the system will be work. So mostly you will be seeing that extremist condition and this one emergency condition are treated as a single conditions. Okay, so you will have normal, alert and restorative condition as a whole. All right, so introductory portion is that yes, in the last few lectures we have also talked about SCADA and EMS system, and in SCADA you must be knowing that what is SCADA. SCADA is basically a software which is supervisory control and data acquisition. So electric utilities have installed extensive supervisory control and data acquisition, that is SCADA, throughout the network to support computer based systems, right? So we have several computers that can be treated or that can be operated with the help of SCADA. Now the data which is used for numerous applications such as system monitoring and economic operations, security assessment, control of generation, all these processes can be taken care of with the help of SCADA, right? And this is basically the data which is utilized, right? Now before any assessment is made for control action is taken, now a reliable estimate of existing state of the system must be determined. Okay, so this is very much important. So why this? And for this purpose, the number of physical measurements cannot be restricted to those quantities required to support the power flow calculations, and moreover, error in one or more of the input quantities can lead to useless results, right? So if you have data, basically all the data is not of use, right? So there are some bad data is there. Bad data could be treated as just like irregular or inappropriate measurements are there, so that is treated as bad data, redundant data. So that data has to be removed from your whatever the data you are having. So this is how SCADA operates. So this is the whole system. Let us say that these are the devices which are connected into the this substation, and these are remote terminal unit, RTUs, and there is PLC, that is the programmable logic controller, and these PLCs are controlled with this PLC these RTUs controlled by this PLC, and actuator, meter, accumulator, all these parameters, all these equipments are there so that the values can be measured. Now this RTU will, what this RTU do? This RTU basically calculates the values or takes the parameters, and they its main function is to forward this value or these values or these variables, these parameter to the substation, right? Basically that sub LDC, not substation, sub LDC. Now that sub LDC will just upload the data to the server or cloud so that it can be utilized, or it can have access by any of the levels, hierarchical level. And in between there is communication links, and these are basically radio wave, microwave, spread spectrum, and twisted pair, fiber optic, dial-up, leased line. So whatever communication system you have, you can utilize any of those communication system, and that communication system by which this is basically transmission receiver type of network, so that the data is transmitted from here to here. This is receiver, this is SCADA over here, so that you can have the control of this devices by this position, right? So by this position, what you do, this position, this is HMI, SCADA master external controller point, right? So basically this is the control portion, and from this you can control the whole system, right? So basically this is a potential transformer, current transformer, measured values over here are P, Q, V and I. So this is the one of the example for which the quantities can be measured. Now in practice, other conveniently measured quantities such as P, Q and line flows are available but cannot used in the power flow calculations. So P and Q are known, but it obviously it can not be utilized in power flow calculations, right? To avoid the unavoidable error into the measurement are assigned statistical properties. Such limitations are removed by the state estimation. So this state estimation is utilized for removing these kind of limitations, where we can use weighted least square calculations. Now weighted least square calculation will be utilized over here, chi-square method will be utilized over here. Okay, so by using these methods we can remove these limitations. Lastly, you have gross error detection in the course of state estimation, which are filtered out over here. Now state estimators allow the calculation of the variables of the interest with the high confidence despite the measurements that are corrupted by noise. So you have communication system, so it is obvious that noise will be there into the system, rightly. Similarly, despite of the measurement that may be missing by grossly inaccurate, so bad data, inappropriate measurements. So despite of that also you can have the actual calculations, right, by the state estimation process. Now the states which I was talking about earlier, these are state X, which is defined as voltage magnitude and the angle at the bus. So voltage is the actual amount of voltage which is the bus is carrying, and angle is actually V angle delta, right? So X is basically V1, V2, V till Vn, and delta 1, delta 2 till delta B. So we are just saying that we have n number of buses, so n number of buses have voltage and delta over here. So it can be written as Vi is equal to Vi e to the power j delta I. This is the one form in which it can be represented. All the variables of interest can be calculated from the state, and the measurement mode is this one, Z is equals to Hx, right? So we generally not directly observe the state, but we can infer it from the measurement. So yes, obviously the system are there, you have parametric values over there. So depending upon those parametric values, you can have these measurements. So depending upon the measurement, you can infer the state of the system, obviously not directly, but you can have this measurement. And secondly, by the measurement are noisy, gross measurement error, communication error, are channel outages. So depending upon these channels outages and gross measurements, these measurements are become noisy in nature, right? Now for understanding the system or state estimation, we will take an example of 3-bus power system. In this, you can see that there are 3 buses. Bus number 1 is there, bus number 2 is there, bus number 3 is there. You can see that this is generator 1 over here generating 65 megawatts, generator 2 G2 generating 35 megawatts, and there is a load of 100 megawatts, right? Now as you can see, the total load is total generation is equal to the total load over here. So you can have a proper power flow equation over here. So here you can see that from bus 1 to bus 2 60 megawatt is transmitted, bus 1 to bus 3 5 megawatts is transmitted, and bus 3 to bus 2 this one 40 megawatts is transmitted. Now for calculation point of view, we can have meters over here. So this is actually the meter location. So you have meter 12, meter 13 and meter 32. These are basically water meters. Okay, so they will calculate the amount of power flowing in that line. Now per unit reactance of 100 megawatt base given for each line, that is x12 is equals to 0.2, x13 is equals to 0.4, x23 is equals to 0.25. Now only we can have, basically 3 watt meter method, 2 watt meter method. So you can have only 2 of these meter readings are required to calculate the bus phase angles and all the loads and generation value properly. So M13 value is this one, 5 megawatts, because 5 megawatts was being transmitted. M32 is 40 megawatts, and calculating into the power per unit, it comes out to be 0.05 and 0.40 per unit. Similarly for F31 and F32, it comes out to be same 0.05 and 0.4 per unit. Now calculating the angles, considering the third bus as swing bus, you have theta 1 and theta 2 as this much, that is 0.02 radians and minus 0.1 radians, right? Now what we need, so if you want to have state estimation, what do you require, right? So a procedure that uses the information available from all the 3 meters to produce the best estimate of the actual angle, line flows and the bus load and generation. We require only these some values. Okay, so we have 3 meters providing us with a set of redundant readings with which to estimate a 2 state, that is theta 1 and theta 2. These are basically the states which are being determined over here. Now we say that the readings are redundant, since as we saw that earlier, only 2 readings are necessary to calculate theta 1 and theta 2, and the other reading is always extra. So yes, we have 3 meters, and out of these 3 meters we are utilizing 2, because we can have the state estimation from 2 meters only. Now you can say that the third one is extra. Obviously it is extra, but you cannot discard it, right? Why? Because it also, although it has some information, okay, so if you have some information, you cannot discard it. So the extra reading does not does carry some useful information, that is a useful information may be there, and ought not to be discarded. It should not be discarded, right? Now firstly is the method of least square. So what is this? The acquired data always contains inaccuracies during measurement and or transmission. So whatever the data is measured, whatever the data is acquired, so although it could have some noise, some errors would be there, could be there, right? So depending upon that, we say that these must have some inaccuracies. So the best estimate are chosen so as those which minimize the weighted sum of the square of the measurement error. So basically you have to minimize the error, and here what we will do, we will be minimizing the weighted error, weighted sum of the squares of the errors, right? So if we talk about this one, method of least square, so mathematically z is equals to hx plus e. So this has to be minimized. What is z over here? Z is the measurement vector, h is the system model relating state vector to the measurement sets, and x is the state vector which we talked about earlier. So voltage is there, magnitude and angles are there. So e is the error vector associated with the measurement set, right? So it is the error vector which has to be reduced from this equation, because earlier you know that this was only z is equals to hx, but now here we have to minimize the error so that it could be equal to this one, right? Normal Gaussian distributions, you must have studied this Gaussian distribution in your school, that is 6th standard or 11th standard maybe. So this is the standard deviation or Gaussian distribution curve. In this, if the measurement error is unbiased, you know you are just calculating the error. So if the measurement error is unbiased, the probability density factor function, that is PDF, probability density function, this one of chi is of zeta, not chi, of zeta is usually chosen as a normal distribution with zero mean. So here PDF, that is it is a function of this one, right? And it is equals to 1 upon sigma under root of 2 pi exponential 1 minus eta square upon 2 sigma square. So what is sigma over here? Sigma is the standard deviation, which is standard deviation. This is standard deviation, and the sigma square is actually the variance, right? So yes, the sigma is the standard deviation and sigma square is variance of the random number, and this is the actual distribution. Okay, so here you can see that this is 0 over here, and you can have 1 sigma, 2 sigma and 3 sigma, and these are the basically quartiles. Okay, so this is 100% over here, and the whole data is divided uniformly over this one, right? So this is normal Gaussian distribution function. Now state estimation problem development, how you will develop the state estimation problem. So that problem which we have taken has to be solved with this state estimation problem. So classical approach is there. So we have weighted least square method. So we have just talked about this, and depending upon this, it is actually minimum of jx, it is equals to summation of I is equals to 1 to m zi minus hi x square upon sigma I square, and we have to minimize it. So that minimizing jx, j is the weighted least squares, right? So that is equal to z minus hx transpose multiplied by w multiplied by z minus hx, and all these are basically matrices over here, right? So you see w is the weighted matrix, so the weight which will be multiplied by the errors over here. This is the reciprocal of the error variance, and in case of linear system, that is hs is equals to capital Hx. So if you have normal linear system, this condition will be fulfilled. The weighted least square estimate of x is basically given by this one. This is again the matrix. So x estimated is equals to g inverse h transpose w z. What is this one? G over here, g is the h transpose w h. This is actually known as gain matrix, right? So this is how the problem of system estimation is carried out with the help of classical approach, that is weighted least square method. Now you have two special cases. Firstly, fully determined cases, if you know what the cases are there. So first is the fully determined case. Under that condition, when what will be the fully determined case? When the number of measurements is equal to the number of state variables. When you have measurements, state variables equal, this will be fully determined case, and under that condition you will have this condition, that is x estimated equals to h inverse z. Okay, so second one is the underdetermined. Obviously it is equal when your estimated number, when your number of measurement is smaller than the estimated, when you estimate more. Okay, so under that condition, you know that that will be treated as underdetermined case. So under this condition, this one, that is x estimated, will be equals to h transpose inverse multiplied by z, right? So coming back to that problem in which we have considered 3 buses. So under that condition, we were having 3 meters, 3 water meters. So under this, you will assume that all the 3 meters have the following characteristics. Firstly, meter full scale value is 100 megawatts and the meter accuracy is plus minus 3 megawatts. These two conditions are fulfilled, or these 3 conditions are applicable for all the 3 meters, right? This is interrupted to mean that the meters will give a reading within the plus minus 3 megawatts of the true value being measured for approximately 99% of the time. So we are just considering that from 99% of the time we are getting true value. Okay, so true value within the range of error of plus minus 3 megawatts. Now mathematically we can say that the errors are distributed according to a normal probability density function that we have just seen in the previous slide, and with a standard deviation of the sigma, that is 3 sigma is equals to plus minus 3 megawatts. So sigma is basically standard deviation. So deviation is basically from the actual value deviated from the value which is deviated from the actual value. Okay, so hence the metering standard deviation sigma is equals to 1 megawatt, and in per unit it is 0.01 per unit, right? Now to derive H matrix, you have to calculate H matrix over there, right? So we need to write the measurement as a function of the state variables, and that is theta 1 and theta 2, that are the measured value of first meter and second meter. Now these functions are written in per unit as m12, which was in terms of these state variables, that is 5 times of theta 1 minus 5 times of theta 2. m13 comes out to be 2.5 times of theta 1, m32 comes out to be minus 4 theta 2, right? So now we have these equations, that is a meter values in terms of our state or basically states only, that is x, right? Now H, by calculating all these things, you will find that H matrix is 5 minus 5 minus 5 2.50 0 and minus 4, and the state variables are x, which is state variable matrix, which is equals to theta 1 and theta 2. Now you have to calculate the covariance matrix, that is W, which is 0.0001 0 0 0 0 0.0001 0 0 0 0 0.0001. This is the covariance matrix, that is W. Now you have H matrix, you have W matrix, you have X matrix, you can calculate the states. Our least square best estimate of theta 1 and theta 2 is given as this one. So theta 1 estimated, theta 2 estimated. Now you will just put all these values over here. This is H transpose W inverse, then H multiplied by H transpose W inverse X matrix, right? So when you will calculate all these matrices, multiplication is taken care, you will find that theta 1 estimated, theta 2 estimated to be this one, 0.028571 minus this one. Okay, now we can have the actual value. So firstly we have estimated and secondly we have actual value. So here you can see that it is actually sending 68.5 megawatts. This is sending 30.6 megawatts, and this meter value is and this line is taking 37.7 megawatts, and load is utilizing 99.1 megawatt, right? And similarly you can see here it is not 5, it is 7.1 megawatts. And what is basically it is the difference between the estimated and the actual value, right? So how good are the estimates? So basically what you have calculated, how much they are near the actual value. So what criteria, it depends upon what criteria for acceptance is reasonable. So what you are, whatever the method you are utilizing, whether it is reasonable or not. So this takes this has to be taken care of, right? If a grossly erroneous meter reading is present, we can detect that the fact and identify the bad data measured. So you can have the analysis of bad data measurement. So what is bad data? Basically the inappropriate reading. So that reading could be some due to the human error as well, or secondly it could be due to the inappropriate meter that is being utilized, right? Now these questions can be answered within a quantified level to confidence by attaching a statistical meaning to the measurement errors in the least square calculation, right? So least is under the least square calculation, this statistical meaning can be added over there. Now you have bad data, so that bad data could be tested for how much bad data is there. So each estimated error is a Gaussian variable with zero mean in this, and this weighted sum of the squares of this has a chi-square distribution, that is chi k square. So this is actually given over here, where k is the degree of freedom, how much degree of freedom is there. So you can see that there are several k over here. So this one k1, k2, 3, 4, 5. So this one is for k1, right, red one. This is for k2, and this green one is for k3 over here, right? So k4, you can see as the k is increasing, the curve is getting downwards. Now we have a hypothesis over here. So hypothesis testing has to be carried out. So these are the hypothesis testing probability to that jx must be greater or tj, and it must be equals to alpha. What is j? That is the measurement residuals, and alpha is the significance level, and tj is the threshold value. Okay, so this is for bad data testing, right? So power system state estimation. Now finally we will have power system estimation. That is if we are having state estimation, though in the power system, how you can say that states are being measured. So states will be state variable in power system will be voltage magnitude and their phase angles, that is V angle delta, right? So they combiningly can be treated as state variables. Now we have two kinds of input as well, that is first one is data, and this data will be value of real power and value of reactive power. Okay, so P and Q measurements are the two kinds of input, that is data to the system. And the second one is state information, status information. Status information is basically just like the position of circuit breakers, isolators, all these. So on and off conditions of switching devices. So these are basically switching devices. So whatever if it is on, you can have value 1. If it is off, you can have 0 value, right? Now number of actual measurement is far greater than required. So yes, if you have to calculate the state or do the state estimation in the power system, the number of actual measurement must be far greater than required, because you will be having bad data into the actual readings, and you have to reduce, or you have to redundant, or you have to just strike out the bad data, redundant data from this available data, right? So unlike the earlier DC example, the measurement equation, that is Hx, are non-linear in nature. So firstly we saw that this was linear, but actually it is non-linear. Now common technique for to calculate the gradient of Jx and force it to 0 using Newton's method. So it is actually the Newton-Raphson method. You must have studied this Newton-Raphson method for load flow analysis, right? So there were several other methods, just like Gauss-Seidel method was there, and fast decouple method was there. So similarly in that, Newton-Raphson method was also there. Okay, so these are the references which were taken for preparing these notes slides. So that's all for this lecture. Thank you. Jai Hind.